Hello, I'm Omar and I'll be talking about the Deep Learning on Trajectory Images fourth year project along with my partner Santosh. Our project aims to classify unmanned aircraft as either fixed or rotary wing drones, or as birds using their simulated trajectories. To increase public safety, there is an urgent need to track and identify unmanned aircrafts. There have been instances in the US, the UK, and Canada where drones have collided with planes. This demo will first go over how the radar simulations were produced using the StoneSoup open source framework. Then we will discuss how to use machine learning and deep learning techniques to make an accurate classification on the aircraft.
We use raw GPS data as the basis of our model. The data contains the trajectory data of a random drone. We use data for multiple drones. This is an example of the 2D projection of the GPS data of a random rotary wing drone. In the real world, it is hard to track a drone perfectly. Two main reasons for this is because there are external factors as well as missed detections. External factors can include an error with the tracker that leads to tracker creating random inaccurate detection. The tracker will think it is tracking a drone when in reality it is not tracking anything. This is also known as noise. To mimic noise, we use StoneSoup to add clutter. Clutter for this project resembles that external data. As shown in the image, the green dots spread across the image is the clutter. The blue dots are the measurements, which are the detection. In the real world, when a tracker identifies a drone, it marks a detection. Unfortunately, a tracker will not be able to track a drone perfectly. Since we are using our raw GPS data, which is referred to as a truth graph and has perfect tracking, we remove some detections to symbolize potential missed detections in the real world. Clutter and measurements were both added to make this model more realistic.
From the previous simulation, we have a bunch of detections and clutter that are generated near the ground truth. It is now time to create the track. First, the initiator will determine where the track starts. Then a hypothesizer will determine where the next point is given the detections. As seen here with the red line, the track is close to the ground truth, which means the tracker is doing a relatively good job in identifying where the drone is in the presence of false alarms. These tracks will be used to create subtrajectories that are the inputs for all our models. So far, we have shown all our simulations as 2D figures, but in reality, a drone or a bird actually has an associated altitude component. The following simulation shows the same rotary wing flight path, but incorporating the altitude feature. We can see that in the second loop, the rotary wing drone increases its altitude, and at the end, it comes back to the altitude it started at. This could not be seen in the original 2D projection, as it seemed like the rotary wing drone was at the same altitude the entire time. The track is also projected onto a 3D plane, which means it has an associated altitude as well. This will be used as a feature for our machine learning models, which Santosh will talk about next.
This is a 3D projection of the rotary wing drone with the truth graph, clutter, measurements, and track. In the real world, a drone can move in any direction, so a 2D projection would not be realistic. These 3D simulated graphs, compiled using StoneSoup, can be broken down into 6 features. These features are the estimated latitude, longitude, and altitude, as well as the estimated velocity for each of these 3 directions. Unfortunately, in the real world, a tracker cannot track a drone indefinitely. It can realistically only track a drone for a couple of seconds. Since our graph spans over a couple of minutes, in order to make it more realistic, we broke the graph down into 40-second segments. Each segment contains a 40-second subtrajectory of the original graph. The graph shown on the screen is the original graph before being broken down into multiple subtrajectories. These subtrajectories were used to create, train, and test our machine learning models. The machine learning models were used to classify the type of drone using the value 1 for fixed wing drone and the value 0 for rotary wing drone. We tested 3 different models in order to determine which model was the most ideal for this issue. We used a support vector machine, k-nearest neighbors, and a decision tree. In order to optimize these models, a hyperparameter was used and updated. For the support vector machine, the hyperparameter is the kernel, which controls the shape of the model. This value was set to linear. For the k-nearest neighbors, we use a k-value of 5, which means when classifying a drone, it looks at 5 drones with similar trajectory paths and classifies it as similarly to those drones. Finally, for the decision tree, we found that using 10 as the depth of the tree produced the best results. These three models were tested by comparing accuracy, precision, recall, and the F1 score.
I will now go over the images of the two classes. The trajectory is broken down into 40-second time segments known as subtrajectories. We use the x and y positions in each subtrajectory to create the images. On the screen right now are the images of the rotary wing subtrajectories. As you can see, they're smaller and they include images where the drone is hovering, like this image right here. Next, we can see the images of the fixed wing class subtrajectories. Clearly, we can see from these images that the subtrajectories are longer since they cover more distance. The difference between the two images will be key to training our deep neural networks.